Welcome to CO2 Mondays with Trevor. I'm your host, Trevor Matthews. And today I have a special guest with me, and we're going to have a great conversation on CO2 compressors. My guest is Phil Boudreau from Bitzer Canada. And Phil has so much experience and knowledge in refrigeration, and I'm really excited about this conversation today. Phil, welcome to CO2 Mondays with Trevor.
Thank you very much, Trevor. Pleasure to be on.
Awesome. Well, why don't we start off and have you introduce yourself to the audience? Talk about your experience in refrigeration in the industry, as well as when you first were introduced to CO2 refrigeration.
Sure. So again, my name is Phil Boudreau. I've been in the refrigeration business, started in wholesale many years ago, 85, 86, and spent several years in wholesale. Gradually got into the technical part of it, learning about the components and systems and things like that. Took a real interest in that. I was one of those guys that used to grab a part off the shelf, take the instructions home and read them, because I know one day there's going to be a technician that comes in and he's going to say, Phil, how do I use this? How do I wire it up, or what have you? And I want to know what I'm talking about, or at least, have a bit of an idea what it is that we were selling at the time. So over time, I ended up, I did more reading, taking courses, things like that. I started writing for Mechanical Business back in the early 90s. 92 was the first article that I had done for them. It was called HPAC magazine back then. Been writing ever since, actually. I was there just to fill in for somebody else who couldn't write an article that month. And here we are years and years later, still writing articles. So I also taught at Humber College for 11 years. This is their after hours continuing education program. So what I taught there was systems, balancing, components. We got into things like pipe sizing. We got into things like pressure enthalpy diagrams. We got into psychrometrics and all those wonderful things. So years later, meaning almost 14 years ago, in fact, I started with Bitzer Canada as the RSM sales manager for Ontario. And what can I say? Once I came on board, like anything else technical, I just absorbed it. We got to learn about our compressors, how they work, and some of the nuances. Like, I like to understand things at the highest level possible. So since then, I've been doing a lot of technical training, a lot of refrigeration articles, things like that, and I continue to learn. And it's funny, once you feel like you've got the basic idea how some things work, then all of a sudden new concepts are introduced, like CO2, and here we go again. It's time to start learning all over again. So what's this transcritical you're talking about? We never had to work with these terms in the past, but it really makes things interesting. And in terms of CO2, years ago, I remember engineering firms, engineers in general, and other people, even end users, would say, why are we even considering CO2? It's just not efficient at all. And, never say never. There's been so many patents filed over the years to improve the viability of CO2 to the point where you can install CO2 systems that operate very efficiently, very reliably, and we're able to achieve the the overall goal of reducing the carbon footprint. So that's basically the introduction for me and where I've been, and we'll see where we're going. But
Yeah, no, I really love that. You've been in the industry for so long, but you're still continuing to learn and continue to embrace the new technologies, because there's lots of people that would be like, I don't want to learn anymore. But what I love about the refrigeration industry, we can continue to learn and grow our knowledge. And CO2 is a really good place to start today for sure.
it sure is.
So let's just get right into it. So Bitzer has been probably one of the largest CO2 compressor manufacturers, I think, in North America, because I've been doing lots of CO2 training over the years, but I've been always seeing Bitzer on rack. Why don't we start off with a little bit knowledge behind Bitzer, maybe their line, and what type of compressors they have for CO2.
Sure. Okay. Well, Bitzer is a company that's been in business since 1934, producing compressors, CO2 compressors. I couldn't tell you exactly when they started producing them, but and that's something I should actually double check. But I believe it was back in the early 90s, if I'm not mistaken. Bitzer has a line of subcritical type compressors and of course a line of transcritical compressors, and they're constantly working to evolve the product line, expand it, um, provide more, improve efficiencies wherever possible. Just the usual part of compressor development.
Awesome.
Yeah.
Awesome. And that is great. What is one of some of the biggest differences between an HFC or a synthetic refrigerant compressor to now a CO2 compressor? Why don't we talk about that?
Well, the pressure capability of the housings for sure need to be greater for CO2. CO2 is a higher pressure refrigerant, higher density. Lubrication is something that needs to be considered with CO2 compressors due to the high solubility of CO2 with oils in general. So, for example, Bitzer uses a BSE 85, which is thicker oil than we would normally use in HFC compressors. If you look at anyone who's opened up a CO2 compressor and compared the cross sections of the pistons, and that'll see that there's a very big difference. That when you take a look at a CO2 compressor, you see this large casting and these little tiny cylinders in there. And this is because the refrigerant has such a higher density than the traditional HFCs that we've been working with.
Yeah.
Running gear, everything else needs to be beefed up for CO2. The motor versus displacement, of course, needs to be adapted for CO2, and not just CO2, but depending on the application range for the CO2.
And what I really like about that, every time I looked into a CO2 compressor, it totally looks different in a way that the components, like you said, are beefier. You look at the wrist pins and they're thicker. Even though the cylinder is smaller, like the components are built bigger. What about the differences between we talked over in the last few weeks about the differences between transcritical and subcritical, but let's talk about the compressors. Is there a big difference between like a transcritical CO2 compressor and a subcritical CO2 compressor?
Yeah, the biggest thing will be, again, the pressure ratings are quite different. So when you get into the smaller, you get into the subcritical compressors, will have pressure ratings of, say, 435, I believe, on the low side and 770 on the high side. But when you get into the transcritical compressors, the pressure ratings are quite a bit greater. So 1,450 PSIG on the low side and 2,320 on the high side. So now with the subcritical, there's also what Bitzer calls this is the medium, or it's designed for the high standstill pressures. We call that the ME series, and it actually has a low side and high side rating of 1,450 PSI. So the big difference between the subcritical and the transcritical, I would say, is the casting. You're dealing with much higher pressures in a transcritical process where we're compressing refrigerant. We're transcending the critical point, which is why it's called transcritical, into the region where you're producing subcritical fluid. And in this particular case, I mean, the compressor needs to be able to work at these very high pressures and produce flow at these high pressures. So
Yeah, and that's really important to understand, that you need to make sure you use the right compressor for the right application. And it's like lots of people say, well, it's a refrigeration compressor, I can just use it in this application. Well, not necessarily. You need to make sure it's designed for CO2. You need to make sure it's designed for that specific application and understand the compressor fully, because I talk to lots of people, have done lots of compressor trainings over the years, and a lot of people don't know that there's compressor manuals. And that's one great thing about Bitzer. When I go into their documentation, you have lots of manuals on the different styles of compressors, and then extra, as well as extra manuals. And that's what a lot of people don't know. They'll get into one manual, but there could be 5 manuals that are related to that one manual, which is very important to understand.
Yeah, I agree with you, Trevor. And the thing is, the manuals are certainly there, but you would never, a technician would never want to make the mistake of assuming that, because they worked on HFC systems for years, that this is just kind of like a plug and play. There are some different things that we need to understand. And, one of the classic examples is is the miscibility of the refrigerant and the oil, or the solubility of the refrigerant in the oil. And over the years, even when we're getting into HFCs and POE oils, they had a higher solubility than their predecessors. So then superheats became even more important. And now with CO2, we can step that up a notch because the superheats are even more important, because we do have to maintain a good balance between the lubrication itself, the lubricity, the viscosity of the oil. If the superheat is running too low, then you dilute the oil, the viscosity drops off, and then we just end up reducing the life of the compressor. So superheats are extremely important. And generally, my experience in doing the training is that a lot of technicians, they're so focused on suction gas superheat that we never really talk about discharge superheat. And discharge superheat is basically going to include the heat that entered the compressor, obviously, plus motor heat and that sort of thing. But if you want to ensure that you've got sufficient lubrication, this is something that should be looked at, is your discharge superheat. So in the Bitzer operating instructions, this applies to HFC compressors, it applies to CO2 compressors. You definitely want to get yourself familiar with the minimum superheats and make sure that you're meeting those superheats. And just because you have, say, 10, 15, 20 degrees, this is just in general, I'm saying, but just because you have superheat there, you can't assume that it's not going to create a problem with the compressor. I've had discussions with technicians where we get on the topic of superheat, and they'll say, "Well, Phil, there's no way there's liquid refrigerant coming back." It's like, well, we don't have to be talking about liquid refrigerant. Low superheats in general will have an impact on your discharge temperatures and your discharge superheat specifically. So it's very important to note those minimum superheats in the software, in addition to maximum operating temperatures, these sorts of things, minimum oil temperatures, and really understand those and make sure you set up systems accordingly.
Why don't we start with transcritical compressors, and what is the recommended superheat for the transcritical CO2 compressors?
Generally speaking, the minimum return gas superheat is 20 Kelvin or 20 Kelvin or 36 degree Rankine. So we could say 36 degree Fahrenheit. And so that's on the suction side. And so that's
for subcritical or transcritical?
both.
Both.
Now, yeah, there is a caveat in the instructions, though, as you can operate lower superheats as long as your discharge superheats don't go below a certain level, right? So, for example, I believe it's 72 degrees Fahrenheit minimum discharge superheat, or 72 degree Rankine is the minimum amount of discharge superheat. So that's kind of how it works. Generally speaking, your minimum suction gas superheat will be 36, call it 40 degrees Fahrenheit or Rankine. But you can actually operate lower as long as your discharge superheat is sufficiently high enough, because again, we want to make sure that we're not over diluting the oil with refrigerant and reducing the lubrication of the compressor. And this is going to depend on compression ratio that the system's operating at, or the compressor's operating at, that sort of thing.
So I know you've been on tons of sites before. What are some of the manufacturers doing to help mitigate having low superheat? Because you just mentioned if you're below, say, 20K or 36 Fahrenheit, that you could start having a lubrication issues. What are some of the manufacturers that you've seen out there? What are they doing?
Things like the way to get the heat up in the system, to get the superheat up, is to use some form of a heat exchanger. Sometimes it'll be just where they pass a pipe through another line that's going to pull some heat through that. Heat exchangers, for example, that could be, in between the gas cooler and the medium temp suction. Heat exchangers that will be between, say, the liquid of the low temp and the suction of the low temp. These are generally, I'll say, relatively efficient ways of superheating the suction gas, because you're not using an external source of heat. It's coming from within the system. So much like using the typical liquid to suction heat exchangers that were used on systems for many years. In fact, there's a lot of systems today, I think, that even the HFCs and HFC HFOs that could really benefit from a use of a heat exchanger like that to get those suction temperatures up.
Yeah, I believe that for sure. Definitely for sure. What about, okay, so now we got to keep a minimum superheat. What about the discharge? Wouldn't that now risk you overheating the compressor as well? So what are they doing for that, or you just got to keep an eye on that? Because I know you don't want to get your oil too hot, because now you can start breaking that down. Is there a limitation on the discharge?
Yeah, there are. So in the operating instructions, the maximum discharge temperatures are published in there as well. So yes, we'll have to definitely respect those as well. And the booster systems are a little bit tricky in a sense that if you look at a typical supermarket type system, you've got a subcritical circuit which handles your low temp refrigerated fixtures. And then you have the medium temp compressors, which will handle the medium temp load, of course, and even flash gas bypass if you're not using dedicated parallel compressors for that. Um, so one of the challenges there is, I guess in the supermarket, you generally have a fairly good balance between medium and low temp. In the event that the balance shifts, for example, if you have a lot of low temp load, a lot of low temp capacity, so now you've got a lot of discharge, a lot of flow with high temperature discharge going into the return, basically, of the medium temp compressors. So that can create a concern. Conversely, we look at the other side of it. If you have a lot of medium temp load and you had very little low temp load, right? And you're running transcritical, so you've got a lot of flash gas bypass. As you're making the flash gas, passing the flash gas from your receiver back into the medium temp suction, it's very normal to have a small amount of liquid form, liquid droplets. And the interesting thing with CO2 is it has quite a high latent heat. And this is the problem. Any liquid that can leave, say, an evaporator, because its latent heat is so high, it's going to be hard to boil off that droplet of liquid. The other thing is that the pressure drop has less influence on the saturation temperature of the CO2. So you would need a lot more pressure drop in the suction line to help flash that liquid droplet off and heat. And the numbers are quite staggering in some cases. I forget exactly what the saturation temperatures were, but in some cases you may need a 10 psi drop in suction just to see a 1 degree drop in saturation temperature, depending on where you're running low, medium, high. But those two things together make, I would say, superheating, making sure you have really good control of the evaporators and good superheating there, and stable. It's got to be stable.
Yeah, and I like that because that's a big difference in like an HFC system to a CO2 system. You do not want a 10 psi drop in an HFC system because your
No.
compression ratio skyrockets. But when you're talking about a CO2, a 10 psi drop is still a lot, but you don't see such a massive compression ratio increase as you would in a HFC system.
Yeah, that's right. And, in CO2 systems, it's not that, the intention is to design for higher pressure drops. The CO2 can, although it may take more pressure drop to actually induce that flashing of a liquid droplet, still the idea, of course, is to design systems to be as efficient as possible. So you're still going to design for those minimum pressure drops. So you're going to have you design for a low pressure drop, and then you have some droplets leaving an evaporator. they're going to show up at the suction of the compressor.
Yeah. Let's get into the oil a little bit because I know oil is something that's really hard for a lot of technicians to grasp, even myself, many, many years still learning oil systems and oil management. But what type of oil do you need to put in these CO2 compressors? Is it the same as HFC? Is it different?
Uh, it's it's a little different. So Bitzer uses a POE oil. The specifically the most common one is the BSE 85. So this has a higher viscosity than a higher base viscosity than you would normally use in an HFC compressor. For example, it'll be 32 centistokes at 40 degrees C for regular BSE 32, as it's called for HFCs. And with the CO2, that viscosity is much higher. And I don't think it's 85, but it's a number that's much higher. So again, the idea is to start off with a higher base viscosity because we know that the refrigerant is going to have this effect of you know solving into that oil and reducing its viscosity. So by using an initial higher base viscosity and having good control over superheats at the evaporator and good system design so that we can further achieve the minimum superheats, and that this is how it works. So that's the main difference with the oils, I would say, is thickness, but it's still a POE oil.
Yes, excellent. And that's really good to know because POE oils as well, same with this, it's very hydroscopic. So you want to make sure you pull a really good evacuation when you're doing a system. And that's one thing about CO2 systems compared to HFCs that I've seen over the years. Even when I was installing a lot of supermarkets, there was cutting corners, not pulling the proper evacuations, not purging. I've done a lot of that in my day, but with CO2, there's no cutting corners when you're installing a CO2 system because you need to be doing it properly. And I just didn't know at the time, but now in my later years, I was doing it properly. Can you add anything to that? And where you see maybe a shift from an, HFC store in the past to new CO2 stores?
Um, uh, One thing is the fact that you're not. It's not like you're taking a manifold set and hoses and connecting it, putting it on a system and taking it off, and a little bit different that way. The CO2 systems generally have their own. They're very well um, guarded in a sense that they have pressure transducers and the temperature sensors and everything, and all this information goes back to a PLC or supermarket control system that gives the technician access to this. Systems oftentimes they'll have actual pressure gauges, even thermometers that are built into the system so that you don't have to be interfacing with the refrigerant that way. So working with the CO2 systems is a little bit different in that sense, I would say.
Yeah.
And the other thing too is CO2. When you get into charging, of course, it's very important that you get a somewhat of a static charge in the system. We have to at least get that pressure above the critical or the triple point, because if we don't, and the pressure is too low, I believe it's 75 psia. If you're down that low or lower, then what's going to happen is you start injecting or charging liquid into that system. It's basically going to form dry ice, and then everything's just going to start locking up. And this is where damage can occur to the system, things like that. So again, it's all in the operating instructions, though. You charge the plant to say 150 200 psig or so, get it well above that triple point, and then once you're above that, then you can continue charging liquid into the receiver.
Yeah, and that's a good point. I've had a lot of people call me over the years, be like, Trevor, I'm on call. I've never worked in a CO2 store. What do I need to do? And it's one thing. Is it above, 100 psi, 150 psi, 10 bar, whatever? You're good to go and start adding liquid into the system. And just
Yeah.
being aware, taking the time to look at that into that manual, because still to this day, all the CO2 training that I do, I ask, have you read the manual for all the components? No. Did you read at least the manual for the compressor? I didn't yet. So it's really important that I really try to push a lot of technicians just to take the time to read these, man, because there's so much gold inside them. There's so much information that, and you got to read them consistently. And over time, what I tell them, you're going to see similar patterns in different compressor manuals. You'll see the same thing over and over again in certain areas. And that's
Yeah,
why it's good to take the time to do that.
it is. And crankcase heaters is another one too. And I've seen systems like condensing units and that where a technician is just planning to fire it up. Meanwhile, the unit hasn't had power. And so if you've got that, you've got a compressor that's got oil in it. As soon as you expose refrigerant to it, that oil will absorb refrigerant, uh, and it'll just continue to absorb that refrigerant. So by not having the heaters energized a day or two, say in advance, can really create some issues, particularly when you start up the compressor. You're just reducing the life of the compressor right from the get-go because your lubrication or the viscosity is too low. And it's going to take a bit of time to get that up to temperature and get that oil viscosity back to a normal level. So I would say make sure those crankcase heaters are warmed up in plenty of time before you do the actual commissioning. And another thing about the commissioning of the CO2 systems is it's always better to do it in steps. Okay, so you
Mhm.
establish a heat sink, so you've got gas cooler fans on, then you start up a medium temp compressor. So now you've established your heat sink for the low temperature stage. So then you can start up a low temp compressor and just commission it in steps, basically. And this is all in the instructions. Uh, Slow change is always better. Then you have the opportunity to make adjustments instead of just firing everything up and just hoping for the best. You definitely don't want to get into doing that sort of thing.
And these are things that you would still even do on HFC systems. You want to plan
It's
it
true.
and do it step by step, because I've worked on a ton of systems that are real low temp. You don't just open it up and let it rip. You adjust that TX valve and then you let it start to drop the temperature. Because if you have a big cement slab, you can't just pull the heat out of there in a second. You're gonna
Exactly.
break it up and stuff. So it is a process, and really getting into these guides and reading them is gonna help you out.
Yeah. Yeah. 100%.
Uh, I had a lot of questions from different technicians, especially here in Ontario on the PRV. So you have on these CO2 compressors now, you have something that I've never seen on the HFC compressors. You got pressure reliefs, PRVs on them. Can you talk a little bit about those?
Yeah, the pressure reliefs are installed, of course, on transcritical compressors. There's actually pressure relief valves on the subcritical series as well. But it's very important to understand that these reliefs do not replace. They're no substitute for your system reliefs. Sizing is totally different. These reliefs that are installed in the compressors are there specifically to protect the compressor casting from overpressure. Things like somebody inadvertently starting up a compressor with a discharge service valve closed. If there's some, kind of a piping issue in the system that is allowing some issue to take place, for example, that the compressor ends up getting full of oil or something like that. Even with the service valve open, that compressor starts up. That pressure is going to rise, and it's gonna rise quickly. So the idea there is to have you know, casting burst protection. And the thing is, another thing to note is with the relief valves that you see on the subcritical compressors, they're actually a part of the service valve. And that relief valve is only in the circuit, okay, when the service valve is closed. When you open that service valve, so the compressor can be put into service, now that relief valve is basically isolated from the compressor.
Wow. Oh yeah, I
Yeah.
didn't know that. See, always learning. I love this. I love this. Always learning. I do have a question, and maybe I don't know if you know the answer to this, but here in Ontario we have TSSA as a body, and I have a lot of technicians ask me, like, do I need to pipe all these reliefs outdoors? Can you comment on that?
Yeah, it looks like that's the way more and more. And there's definitely a few factors here, but more and more systems are getting piped to the outdoors for sure. And all it takes, honestly, is just something goes wrong. Somebody has they've commissioned the system too quickly. So you turn on a compressor and the discharge service valve is closed, and then maybe that relief opens. And the problem with that is get quite messy. In some cases, I've seen situations where the compressor was actually locked up with oil, then the relief opens up. Now you've got a real big mess. So the other part of this is safety is always number one. Making sure the system is safe. But when you have a big mess of oil everywhere, all over your mechanical room, nobody wants that. So yeah, more and more we're seeing systems where local code requirements, even end customers are saying, no, we want to have, relief protection in there and vented to the outdoors. Yeah, so the manufacturers are, I've seen that, Trevor, where manufacturers are actually installing these on their packages remote, so they can be vented outdoors.
Awesome. So I'm assuming that they would build like some sort of header where they would all connect into this header that will
Yeah.
go outdoors. Okay.
Yeah, and then all the rules apply to sizing relief valves. I mean, when you got a big header there, the header has got to be sized to for the worst case scenario. So you'd have to refer to the B52 code in the case of Canada, but also there's the ASHRAE 15 that provides a lot of information on sizing your relief valves in general.
I love that. That is great. Great information. I know I've looked through those before, but it's something that once again I need to revisit. So I get this question a lot as well, is like CO2 changes quite rapidly. Um, do you need any sort of modulation or capacity control on these compressors?
It's very important actually. And in a booster system, as I said, there's always this balance between the medium temp and then the low temp. And then there's also the fact that you could be running, transcritical at one point, and then a month later or two, you're running subcritical. So, once you switch over to subcritical, now the capacity of the compressors goes up, and fewer compressors on a suction group is generally not the way you want to go. I know there's a natural tendency to try and reduce compressor counts on systems, in in order to achieve smaller footprints, things like that. But better capacity control. This is really important with CO2 systems. So variable speed drives, very commonly used on the compressors, especially on the high side, where you do have this balance between, you're feeding it low temp refrigerant from the low temp compressors, refrigerant leaving all the medium temp cases, and the flash gas bypass. But these things all change in terms of flow rates, and your system needs to account for that. If you only have 2 or 3 compressors, it's going to be very choppy in terms of control. So a compressor turns on quickly, then you can expect the suction pressure to drop quickly. And generally with all systems, it's better to have things change at a very gradual rate. No rapid changes are really going to be good.
And that's once again no different with HFC. If you
That's
want a
right.
really good running system, is that you want it staged properly. Because I've seen it many times doing a reno, and all of a sudden you have a large 6-cylinder compressor bang on, and it bangs off, and then bangs on, and bangs off. That's not good. So you do want staging, but it's nice to understand that it's better to have multiple compressors than just one. Is there any other type of other capacity control besides putting a variable speed drive on CO2 compressors?
Well, so first you've got the staging of the compressors themselves. Okay, so there's one form of capacity control, and then you have, you can place a VFD on a lead compressor, a designated compressor on each suction group. And then with the newer style, the newer version of the Bitzers, the TE series, you'll be able to unload these compressors as well. So that'll be another option that will be available soon.
Oh, that's awesome. And would that go in with IQ module? I know when I seen you at the CMPX, you were showing me all about the IQ module. Is that something that will be integrated?
Yes, yeah, the IQ module, you'll be able to use them with the transcritical compressors, with unloading on them, the whole bit. Similar to what we do with the HFC compressors. So you've got a rack controller that can communicate with the IQ module, provide it with a 0 to 10 volt DC, so an analog signal. And depending on that voltage level, it's going to cycle the unloader. So Bitzer Germany's done a lot of work on the algorithms to control the unloading timing of the compressor, so that we get really good control of the capacity of a compressor. So that's an option that's coming.
Now, why don't you elaborate a little bit more on the IQ module and what else it can do? Because I when I seen it at CMPX, I'm like, wow, this is pretty impressive. Do you want to just explain other things that it does and the value that it's going to bring people?
Absolutely. So the IQ module is it's a few things. First and foremost, it's the ultimate in terms of compressor protection, because it knows more than just, you know, discharge temperature and motor temperature, for example, and oil pressure, if it's a, you know, an oil pump model. But in the case of these CO2 compressors, they're not using pumps. But um, so it has access to the envelope. So you would program the compressor model number into it. Okay. And right off the bat, it's a CO2 compressor. The IQ module knows it's a CO2 compressor. Then you would basically parameterize the module and tell it what accessories that you have on the compressor. So because it needs to know what it's going to be controlling. And then from there, once you give the IQ module, once it's powered, of course, and then you give it a run call, basically the module controls all of the accessories on a compressor now. So you no longer need to have, you know, like a normally closed auxiliary contact on a contactor for a crankcase heater and all that stuff. This is all handled by the IQ module. And with the HFC compressors, you can control head cooling fans, liquid injection, your crankcase heater. The module knows if there's a run call, turn the heater off. If there's no run call, the heater comes back on. You don't have these extra wires that are coming back and forth between your control panel. So the wiring is greatly, greatly simplified. It reduces the possibility of wiring errors, just because all you're doing is powering it up and sending it a run call. And aside from that, if you are using the Bitzer refers to this as the very step capacity control method, where we're cycling the unloaders to achieve a certain capacity level. The analog signal needs to be provided via the 0 to 10 volts DC. Well, that's one option. Another way is to control it through Modbus, actually. Then you've got full connectivity. So then the IQ module also provides you with alarm functions, history. If you apply pressure transducers, and I'm talking about HFC compressors, CO2 compressors in general, with the IQ module, using it to its fullest potential, it gives you envelope monitoring, lubrication monitoring, motor winding monitoring, everything. And also, if you try and push a compressor too far, the IQ module will start to actually back off in order to protect the compressor. If you're unloading a compressor, as you unload a compressor, the refrigerant flow rate through it decreases, and then your discharge temperature tends to increase. So in this particular case, the IQ module may make the decision to turn on the head cooling fan, you know, in the case of an HFC compressor. And so that's how it works. It's really cool because you can also connect to it. You could certainly use a cable and use what we call the this is actually a BEST toolkit, which is basically a bunch of connectors inside that, you know, you can plug into different types of IQ modules. One of them being the CMRC, which is for reciprocating compressors. And the other option is to connect via Bluetooth. So now you can take your smartphone, walk up to a compressor, connect to it, and you've got all the performance data on your phone. You can see the actual pressures and temperatures it's operating at, any alarms. If it's off, why is it off? Oh, it's tripped on oil failure. It'll give you that information super quick. So yeah, the IQ module is a pretty exciting product. And we've been actually, this year, we've been moving, selling a lot of the IQ modules, and we've noticed they're really getting specified a lot. So
that's fantastic. So there was something interesting that you said in there, that you have two different styles of oil management. So you said pump as well as, what was the other, splasher? And what's the difference between those so everybody understands? Because I know in your CO2 compressors, the ones that I've seen, they were all like a splasher. It had a ring on it and it goes into the oil. Do you want to explain the differences between those,
Yeah,
if you
that'd be
want?
called like a slinger disc or a centrifugal disc. Sometimes it's called a dynamic disc. It's basically a disc that's directly coupled to the end of the crankshaft, and this disc picks up oil from the sump or from the crankcase itself, brings it up into the top end of the compressor, and it drops into a cup at the end of the crankshaft. And from there, it passes through the crankshaft to the various bearings for lubrication throughout the compressor. So your main bearings, your connecting rods, and everything else that needs to be lubricated get lubricated that way. And you're absolutely right, Trevor. So you look at all of the CO2 compressors that we have here in North America, they do not actually use an oil pump. Um, with the HFC compressors, we do have oil pumps on some of those models. In fact, there's some models where you can, it's optional. For example, what we call the CE4 series, they're available with oil pump or with that disc. So either way, and they're both very good lubrication systems, but we never want to make the mistake of assuming that an oil pump's always better, and some people will tell you an oil pump is always better, but any bearing manufacturer will tell you you don't need to be driving tons of oil into bearings. All you need to do is get it there, and then the bearings will take what they need. So if you're using the proper viscosity and your superheats are correct and everything else, then there's no reason why you couldn't just use a disc. I bring that up because I've heard some say that, well, how can that be any good? It doesn't have an oil pump on it. You get into larger compressors, they need to have the oil pumps because they need some pre-charging of the compressor, if you will, because there's a lot of volume inside that oil management system that needs to be filled up. We need to get the oil from the crankcase through the compressor. Smaller compressors, it's very easy to do with a disc style, and when you get into larger compressors, then the oil pumps just make more sense. So all of the Bitzer conventional HFC compressors actually, all of the HFC compressors, we'll call them conventionals, actually have oil pumps on them. So
Excellent.
yeah.
Okay, so now if it doesn't have an oil pump, how is that oil monitored? Like because on an oil pump, I'll check my net oil pressure and stuff, but is there any devices that you would put on that type of compressor just to monitor the oil?
Yeah, for sure. And actually, I see a colleague just chimed in. He's absolutely right. Little error there. I was just thinking of the 2 and the 4-cylinder compressors, but there are the larger 6-cylinder compressors that are available for CO2, and these actually use oil pumps. So when you're monitoring oil pressure with a compressor, generally you'll look at differential pressure. So pump inlet versus the discharge of the pump, and check for the net oil pressure. With the centrifugal lubrication models, generally you'll use an optical type switch. So, and the idea with the optical switch is it's placed at the end of the crankshaft, basically where that cup is. So it's basically at the end of the crankshaft, in the bearing cover. So that basically fills up with oil when the compressor starts up. And we want to make sure that there's oil there. Having oil there is even more important than the crankcase, actually. I mean, you need to have oil in the crankcase to get it up into that cup. But that's how we monitor the oil. If the oil is in that cup, then from there, it just travels through a bore in the crankshaft and through the various parts of the compressor to lubricate it. So that's how it's monitored with these centrifugal disc types.
That's awesome. Yeah, so that's really good to know because there are these other devices that are on compressors, and you just want to understand how they work. It's super important to do that.
Yeah.
Let's talk about some of the failures you'd seen on CO2 compressors over the years, because I know a lot of the ones that I've seen are due to liquid dilution or flood back. But tell me some of the stuff that you've seen in the field. Let's talk about some failures on CO2 compressors that could be maybe mitigated in the future.
The most common one that I've seen is actually with transcritical compressors that are just running with superheats that are just too low. I have, countless photos and that of job sites where, you look at the compressors and they're just frozen right up. Even the crankcase, everything is just frozen. The superheats are so low. Again, a little bit of liquid leaving an evaporator is all it takes, or too much flash gas versus too little low temp load entering the medium temp compressors. Anything to push that in the direction of low superheat is really harmful to the compressor. And it's very important that the systems designers design with these things in mind, and the different things that can happen, like a balance shift between low temp and medium temp, and what's going to happen when you're running transcritical versus subcritical. The superheats really need to be maintained at all times, during all different modes of operation, and sometimes that can be quite a challenge, but it does need to be considered. Otherwise, you run into these issues with early compressor failures. But I would say, especially with some of the earlier systems, the most common failure for sure has been transcritical, the medium temperature compressors running low superheat. So when you open up the compressor, you'll see things like, the classic is broken valves. It's actually trying to compress liquid refrigerant. That's really bad. But, even if your valve plates are okay, if you've got refrigerant, the superheat is so low that it's diluting the oil. Now you've got worn cylinder walls and rings and everything else, to the point where you wear the compressor out and it loses its efficiency. And eventually will fail because bearings need oil. And if we're constantly, soaking that oil with CO2, then it's going to reduce the life of the compressor substantially.
Yeah, and I've seen lots of that, and that's one of the big differences where technicians will be like, okay, well, I have superheat here, but you need a minimum superheat. It's not like, oh, I got 15 degrees superheat or 15 degrees Fahrenheit or 5K. You need upwards to 20K or 36 degrees, you said, which is very, very important to understand, because even though you have some superheat, it's not enough, because that mixture you talked about with the oil, the way it carries the oil with CO2 is different. So this is something that technicians really need to be aware of. Just because you're reading superheat, is it enough superheat? That's what I'm getting.
Yeah, exactly. Is it enough superheat? And never assume that just because you have superheat that you have enough superheat. And this is of course, this is the case with HFC systems as well. I've seen so many HFC systems out there running low superheats. They're not running liquid necessarily, or there's liquid coming back to the compressors, but the superheat is just so low that the discharge superheat is low. So the oil just has so much refrigerant in it that the lubrication properties of that oil, its viscosity is just too low really to get the job done.
Yeah, I love that. I love that. I'm going to talk about that definitely more. I would like to ask, because we're running out of time. We could talk. I could talk for hours about all this stuff, but I'd like to talk a little bit more about drives on the lead compressor and what you're seeing out there, and what technicians should do to probably get a little bit better at this, because this is one thing that I'm kind of struggling with. uh, Technology's here now. You're going to get drives on compressors, any system now. We're seeing it more and more, inverters, drives, whatever you want to call it, for capacity control and efficiency. But what are you seeing out there, and how can we help technicians get a better handle of this? Because not only on the CO2 system, I'm seeing them on a lot of the synthetic refrigerant systems getting drives on there. So what's your
Yeah,
advice to technicians?
yeah. Well, first of all, don't be afraid of the drive. It's you look at the parameters that a typical VFD uses, and there's hundreds of them, maybe even thousands of parameters that could potentially go into a drive. In actual fact, the parameters that need to be updated are not all that many. In fact, the HFC, so we have done a lot of VFDs on lead compressors on racks where there might be 16, 18 parameters or something like that that get programmed in there. And we need to understand what the limits of the compressor are. So what is the speed range? Because, a drive could take you essentially from 0 hertz all the way up to whatever, even trans-synchronous in some cases. But it doesn't mean we should do that. Of course, the compressor, we have to respect the allowable speed ranges for the compressor and never go beyond that. Understanding vibration is one, perhaps, because when you put a variable speed drive on a compressor, I would say it does tend to increase the possibility that you'll have like a harmonic resonance taking place. And this is basically where, you got a section of discharge pipe that its frequency response basically matches that of the pulsation frequency of the compressor, at a certain pressure and a certain discharge temperature. And in that particular case, if this is the situation, then with most, if not all drives, you can actually program out those, I'll call them the offending frequencies. For example, you could be running a rack and then you get to 37 hertz, and then all of a sudden everything, starts shaking, and it's very resonant. So in that particular case, you can skip it. But one thing I have noticed with VFDs, when someone experiences vibration, they'll generally just assume that the compressor has got a problem. And that's not necessarily the case. There's a few things that can lead to vibration. One of them is reaching the critical the critical length of the discharge pipe. If we do get in that zone where the frequency response of the pipe matches the pulsation frequency of the compressor, we can have an issue there. It could also be mounting. Piping that's forced into place can cause vibration, that sort of thing. So getting back to the drive, the speed range, okay, we need to put that in there. We need to tell it what the voltage is. We need to we have to tell it how to interpret the analog signal. So 0 volts means this, 10 volts means this, and this kind of information gets programmed into the drive. If you run into situations with a VFD where you're running at low speed, say you're down near the minimum frequency, which could be 30 hertz, and you're noticing that while in some cases a drive could stall, it just gets to a point where the drive is not putting enough torque out, and this can become an issue when you're running a system transcritically. So like I said before, you want to have a number of stages for capacity control. And then if you got that VFD on there, let's say a compressor just turned on. Well, now the VFD is going to start to slow down. And as it slows down, the torque, I'll call them torque peaks for every revolution, especially with fewer cylinders, becomes very, I'll say, choppy. And it's less smooth on the drive. And sometimes you do need to provide them with a little extra torque, which is generally done with a voltage boost. These sorts of things, you can consult with the equipment manufacturer. You can consult with us for guidance on that if this type of thing ever happens. Yeah. One thing I've run into also, I've noticed, and this is just drives in general on systems, is it's very important to ensure that if you've got a contactor in series with that drive, that generally you only want to put the most important safeties, I would say, in series with that contactor coil. Okay, other things like a low pressure control doesn't need to go in series with contactor coil. That could actually just be wired in series with the run command of the drive itself. Low pressure control opens, takes the compressor offline. It's very important that when a contactor opens, at the same time, you want to remove the run command from the drive, because a drive is constantly taking in voltage from the mains. It's converting it to through rectifiers, converting it to a DC voltage, storing it in capacitors, and then through like a pulse width modulation and control circuit, it produces a sine. Well, it's a pulse width modulated version of a sine wave. Is basically basically what it is. on the leaving side. And when you remove that contactor or open the contactor, de-energize it, then, and you still have a run command, you're trying to drive a compressor with what is basically remaining in those capacitors. So you want to remove them both. And what will happen to a drive is over time is that there's metal oxide varistors, which are used inside a drive very commonly. And if you, every time you do this, if you open a contactor and that VFD is trying to control a compressor, it's very hard on those. They basically overload, overheat. You do that a few times and then you're just going to have a drive failure.
Yeah, and that's something you said even at the earlier there, is that you need to understand these drives that you're installing, understand those, as well as that application for those compressors, because you could be working on one compressor that has a different range than the next compressor. So
Yeah.
you
Oh,
really
yeah.
want to understand both the drive itself and the compressor, because it's so important. Take the time to learn. I know this is the hard part, technicians, is learning these new technologies. But after you learn it, you're going to be like, wow, I should have
Yeah.
been doing this years ago, because
Yeah.
this makes the system so much more efficient, very easy to use, but it does take time. You need to learn it, just like refrigeration.
Yeah,
So,
exactly. And why, and so why are VFDs being installed on supermarket systems that are well, we know with the CO2 side, some form of capacity control is essential. Uh, it's always important, I would say, but on the CO2, it's extremely important. It's critical, in fact. But whenever you have a VFD, or in this case, for example, unloading with an IQ module, what it allows us to do is really cut out the cycling of the compressor. It also allows you to operate the rack at a net higher suction pressure. So if you can increase your saturated suction temperature of that system, now all your compressors on that rack, even the non-VFD compressors, will operate more efficiently. Now your suction pressure can operate at a higher level. So this is where the efficiency is going to come from. So do it for efficiency reasons, good control, and the whole bit. So
awesome.
you're right. Understand the speed range. Generally with the drives, you can program a maximum power input to them, the maximum amperage, that sort of thing.
Yeah,
In
Phil.
Europe, yep, in Europe they actually have what they call a Varipack drive. We don't have these here in North America yet. Well, actually, I believe we do, just in a lower voltage, but nothing in a 575 yet. But I'm really hoping there's going to be a day where we see those, because I'll tell you, with that drive, you program in the model number and it knows everything about that compressor.
Wow.
It basically parameterize it. It's almost that easy. A
Wow.
little more to it than that, but
Yeah.
it's basically that simple.
I
So
love it. Phil, I want to thank you so much for taking the time to talk about CO2 compressors with us. I've learned a bunch today from it, so I want to thank you so much. We do have a few questions. This is what I like about doing a live training. If you don't mind, we get a few more minutes to ask you a couple of these questions. Okay, we got one question here. What about short suction runs on package units, I guess, to keep the superheat high enough for full coil utilization? I'm guessing this would be a superheat
yeah.
question.
Yeah. So if and this is again a case with even with HFC systems, if you're trying to fill up the coil as much as possible, the evaporator, so you're going to operate it, you want to try and operate at that lower superheat. It gives you perhaps higher efficiency, more effective use of that evaporator. But on the other hand, now we have to consider what we're doing on the compressor end. We still have this requirement to ensure that we meet the minimum discharge superheats, or lubrication becomes a problem. So we don't want to be trading efficiency for reliability. So in situations like that, some form of heat exchange, I would say, is needed for sure.
Awesome.
And when setting those superheats too, it's important to make sure the superheat is stable. It's generally speaking, you try to work at lower superheats, then you can lose stability of the coil as well. So
Yeah, no, that's some great points. Another question here. Can we do hot gas bypass with CO2?
I don't see why not. Hot gas bypass for capacity control.
Yeah,
In theory, I don't see why you couldn't do it. I haven't seen it done myself.
yeah, me
But
neither.
it's the thing with hot gas bypass though is and I've probably said this more times than I can count over the years, but I think hot gas bypass is one of those things that's probably gotten a lot of engineers out of trouble, in a sense that you can have a system that's oversized. And then just by having a hot gas circuit on there, now you're feeding hot gas into the coil, and then your
Yeah.
expansion valve is opening to offset it. So, you could actually size them. You could get them to the point where you're running a system with no load on it, if you got enough hot gas. But the point is, we're trying to design systems nowadays for higher efficiencies and that. And with hot gas bypass, that works against that concept. Generally, just dumping hot gas into an evaporator for a false load is not efficient. So you'd be better off using variable speed technology, unloading via an IQ module, that sort of thing. That way you can lose the capacity, shed some capacity instead of wasting it,
Yeah.
because you're still going to be paying for all that power input to the compressor with hot gas.
Well, there's a couple more questions in here. I'll email these people on those questions. So, Phil,
Okay,
I want to thank you so much for taking the time to talk to us today, and I hope to see everyone at the next CO2 Mondays with Trevor. Thank you so much, everyone.
my pleasure. Thanks, Trevor.